I'm going to bring up our speaker now, Frederic. I asked him before the talk if he were a tree, which tree he would be. If you ever had that question asked, it's an odd one. I did it on purpose. He was a trooper. He told me oak. So let's welcome to the stage, Frederic. And a round of applause, please.
Oh, looks like this is not set up right. 1 second. All right. Sorry about that. All right. So before I kind of get into the meat of the talk, I want to start with a short story about the history of computing. So I want to start in 1971. Does anybody know why this is a significant year for history of computing? All right. So computing history is just about to be written because the Intel 4004 is about to be released. Why is this significant? This was the first commercially produced chip. So this is truly, the year that computing as we know it today started. Fast forward to 1974, and again, Intel writes computing history. And why this time? Well, this time they released the infamous 8080 chip. And why is this very significant? Well, it's very significant because in just a matter of 3 years, we went from 2,500 transistors in this chip to 6,000. And then once again, fast forward to 1978, and Intel releases the 8086 chip with 29,000 transistors, right? And so this is something that one of the co-founders, Gordon Moore, actually described over 10 years before this, which he described as Moore's Law. Initially, he kind of stated that transistors were going to double every year going forward. Around this time, he recanted his statement and said that from here onwards, transistors are going to double every 2 years. And generally, this actually continued to be true throughout computing history until now. And why is it stopping now? Well, the problem is, and this is kind of where we're at today, and actually, this beautiful, beautiful machine that I'm using here uses like 5 nanometer technology. So our transistors are now 5 nanometers wide. Intel predicts that by 2030, they're going to conquer the 3 nanometer technology. And so this kind of begs the question of how small can we actually possibly make a transistor, right? So how much longer can we actually increase computing power by basically just waiting it out, right? The general consensus is that we probably can't make it much smaller than a single atom. Assuming this is actually possible and we can actually manage to do this, which is also not necessarily clear, but let's assume for a second that a single carbon atom, we managed to figure it out somehow to lay it out on a wafer, and we can actually get a single transistor to be this small. How much time do we actually have, right? Well, if we actually, like I said, if we actually manage to figure this out somehow, we have 8 good years ahead of us, and at that point, we're just at atomic level size transistors. And so ultimately what this means is that even though this has been predicted many times that Moore's law is ending, now we're actually hitting the physical limits of what could be possible. So Moore's law is actually finally ending. So as software engineers, we kind of have a problem, right? No longer can we rely on just waiting it out for 2 years and our software kind of magically becomes faster. or we can stick more of our software onto similar hardware. And so what this means for us is that as software engineers, as the software engineering discipline, we actually have to make better use of the hardware that we have. And so that's essentially what I'm going to be talking about today. My name is Frederic. I'm the founder of a company called Polar Signals. We are in the performance computing space, so surprise, surprise. So for the past couple of years, I've been kind of thinking about this entire space and building tooling in order to help us build better, more performant software. I'm a longtime maintainer of the Prometheus monitoring project, if you may be familiar with that, as well as for a long time I was a technical lead for the Kubernetes project. Generally, everything databases, distributed systems, performance engineering is my thing. So that's me. So I generally say that there are 3 rules to improving software performance. The first one is we actually have to measure in order to figure out what's even worth optimizing. If we don't measure, we're at best kind of poking in the dark, right? Once we've figured out through measurements what is actually worth optimizing, we need to benchmark it. And in this case, I mean kind of taking the piece that we figured out we want to optimize and write a small program that we can iterate on so that we can quickly understand whether what we're changing is actually working. And third, and this is kind of a cycle between 2 and 3, we actually have to optimize. We actually have to do the same task doing less, right? And this is where the hard part starts. But before we can do anything, we actually need to profile our software. And profiling is really as old as software engineering itself. It's basically always been around. We always needed to understand where our CPU cycles are being spent. But now it's not just databases. Now it's not just systems-level programming that needs to or not just high-performance computing that needs to be very rigorous about this. Now we all actually have to make very much use of our hardware. So again, we perform profiling in order to understand what's even worth optimizing in the grand scheme of things. And this is one of the things that we happen to work on at Polar Signals. But originally, I think the most interesting approach to this was described by Google in a white paper they called Google White Profiling, where they described how they're always profiling their entire production infrastructure all the time. And aside from describing how they were doing this, they were primarily describing all the amazing benefits they were getting out of this. First and foremost, they always have performance data available whenever they want to improve performance of software. And it turns out at Google scale, or really this applies to any of the hyperscalers, when you optimize away 4 or 5% of your CPU time, that means you don't have to build data centers, right? Like for us, maybe it means that 5% less 5% less CPU time on a server, but not building data centers, that's something very tangible, right? And so ultimately, when I originally read this paper, I concluded profiling is really just as much observability as metrics, logging, distributed tracing, because the reality, just like with metrics, logs, and tracing, is with profiling, you're always going to want exactly the data that you don't have. And so that's why, exactly like with metrics, logging, and tracing, you always have to profile your production infrastructure. And more importantly, and this is kind of what Google described in this paper, you actually have to have a profiler that does this all the time, right? With low overhead and profiles absolutely everything in your infrastructure. Because if you're only profiling individual pieces, or the kind of traditional method of profiling is that you look at one process for a 10-second period of time, right? You don't even know whether that interaction that you want to optimize is even going to happen in that time. whether garbage collection is running, you don't have that under control. Whether that pathological user interaction is happening, you don't have these things under control. And so you have to have a profiler that is always on. And this was kind of one of the statements Google was making in this paper. Now, Google kind of has the ability to, they maintain absolutely everything from the operating system to everything that runs on that operating system, right? And so they described that they built a profiler directly into the operating system to do all of this. And that's ultimately the inspiration for one of the open source projects that I happen to work on called Parca, P-A-R-C-A. And we use a kernel instrumentation technology called eBPF to accomplish the same task. And the cool thing about this is now we can do the same thing where we perform profiling on the operating system level without actually having to modify the operating system. I'm not going to go into too much depth about how this profiler works. If you're interested in that, come approach me afterwards. And I'm going to show you on the next slide a talk where some of my coworkers kind of went through all the nitty-gritty details of how this works. Today, we want to focus on everything that happens after we have this data, right? And so this project essentially consists of two components: the agent that runs on every node in your system, and then a central storage that stores this data, but then also symbolizes it. Symbolization you can think of as when the profiler actually captures the raw data, all we get are memory addresses. I don't know about you, but I don't know the memory offsets of my programs to understand where that CPU time is being spent. And so the symbolizer essentially helps us translate those memory addresses over to function names that we as humans actually can understand and can do something useful with. And then ultimately, it gives us APIs for analysis and a UI to explore all of this. Like I said, if you're interested in exactly how this profiler works, I highly recommend checking out this talk that some of my coworkers gave at Linux Plumbers last year. And this talks about all the difficult problems that come with working in the kernel and having to walk stacks and all of this stuff. But like I said, here we're going to kind of just focus on how can we make use of this data. So I want to quickly show a demo of Parca. Hopefully, conference Wi-Fi does the job. So what we're seeing here is at the very top, what we're seeing is just a metrics graph. So this is the same thing as if you were to use Prometheus and you're looking at the total CPU time of a process. But what's different compared to metrics is that we actually see down to the line number where all of this CPU time is being spent. And the really cool thing about all of this is that up here we see kind of the CPU time of each process. In this case, we had a huge CPU spike, so it's kind of dwarfing everything else. But we're actually seeing all the CPU time in our entire production infrastructure. And so not only, we can actually see what's worth optimizing. So in this case, clearly our Argo CD deployment is something that's taking a lot of the resources in our cluster. So this would be the first thing that we should start to have a look at. As an example today, I want to kind of go through an example of optimizing a workload that probably a lot of you run in some sort of fashion, which is if you run a Kubernetes cluster, you most likely are using Containerd. And Containerd, in case you don't know, is kind of the component that manages containers for you on the host. So the kubelet, the agent in Kubernetes, it ensures that using the container runtime, in this case Containerd, is actually running the containers that it's supposed to be running. And we can kind of look under the hood of what this is doing. And one of the things that it does is it ensures that it kind of keeps reporting how much memory, for example, this container is using versus the amount of memory that it's allowed to be using. And what it does for that is it uses this function. Let me make this a little bit bigger. It uses this function that, in this case, happens to use 5% of the entire CPU time of this process just to read this file, to read a single integer from. So when I saw this for the first time, it struck me as this, we probably can do better than this. And so I took this example and extracted exactly what this function does. And we're going to be going through that today. So like I said, I just kind of isolated this, so it's a little bit easier for us to work with. But what we have here is this function that uses the standard library package OS and reads the entire file into memory. And then once it's done that, it parses the integer from the string to be an actual UN64. And like I said, the first thing that we need to do is we need to look at profiling data to figure out what is even worth optimizing. We've done that. Now, what was the next thing that I said? We need to write a benchmark so that we understand where our baseline is. And so when we actually perform optimizations, that we know how much better we're doing, or that we're even doing something better, right? Turns out I myself and humans in general are actually extraordinarily terrible at estimating how code is going to execute. That's not really our fault. Sometimes this is just very unpredictable. And so we have to measure in order to understand whether we're actually improving or making things worse. So we're going to start with writing a benchmark. And in Go, this is very nice because all of this is built into the standard tool set. But the reality is, of everything that I'm showing today, while I'm using Go as the example, because it's just a language that I'm very comfortable with, the equivalent things that I'm showing here work in other languages. So there are benchmarking tools in other languages. And basically, all of the optimization techniques that I'm going to be going over today work in one fashion or another in other languages as well. So we're going to start with benchmark read uint, and then GitHub Copilot already knows what I'm about to do. So I'm going to just do that. And just to be able to kind of consistently run this test, I actually have a test file that just contains a number that I actually took from a real production machine, so that we can kind of consistently use this for benchmarking. So I think it actually didn't do everything quite right. So this is lowercase. And we want to read from test data /u. And just because I'm kind of foreshadowing what's going to be the problem here, I'm also going to be reporting allocations. We want to not look at the result, but we want to check the error. Sorry? Thank you. All right. So now we can actually run our benchmark. So what we're doing now is, and just for explanation, the loop that I was writing is actually something really interesting that the Go benchmarking toolchain has that automatically kind of runs multiple cycles of this benchmark in order to generate statistical significance. And we can see that here, that it kind of ran about 170,000 iterations every time. And then I specifically also instructed it to do that 5 times. And we can see that this right now takes about 7,144 nanoseconds there. And we can already see where we have a constant number of 5 allocations for every operation. All right. So this is kind of our setup, right? We have identified what do we want to optimize, what's worth optimizing. We've written a benchmark. So let's go back to the presentation to learn what to do next. So now we actually need to optimize this code, right? And it's no coincidence that I'm using this particular example. So we actually run a weekly stream at Polar Signals where we take popular open source software and try to optimize it in order to save the world some CPU cycles, hopefully contributing to not making the end of Moore's law just as terrible as it has to be. So in general, and like I said, everything that I'm showing today, there are definitely lots more optimization techniques, but all the ones that I want to go over today are quite generally applicable to many other languages. And the first one people tend to not want to hear because it's not a one-size-fits-all solution. The first one that you should always kind of think about is whether the approach that you're taking is actually kind of the best one that you can take. Are you actually using the right data structures for the task? Are you actually using algorithms whose complexity match the goal that you're targeting? And only then, when you've actually done this, only then do you go on to the other optimization techniques. So the first one, and I kind of started alluding to this already, the first one that you're always going to try to avoid is allocations. Allocations are just very, very expensive for our computers to do. And so I want to look at several kinds of optimization techniques in order for us to avoid allocations. The first one is escape analysis, and that's the one that I'm going to dive into in a second. But all of these we're going to be covering in just a second. Before I go back to our example, I want to show one of the examples where we were optimizing actually Kubernetes itself on the stream. We identified that one of the most expensive things that it was doing was kind of reconciling mounts locally against the expected state. And it was doing this in sort of, you can think of it as a kind of a hot loop. And the most expensive thing in doing this was iterating over the map. And it turns out, in order to understand why this was bad, we actually need to understand how maps are implemented in Go. And it's quite similar to how most maps are implemented, like the first one that we all learn about when we start programming. It's just a hash map. So we hash the key, and we find out which bucket we should insert this key into, and then we do that. Well, it turns out, in this particular case, we only had 100, or in the order of hundreds of elements in this map. And so the only thing that we were using this map for was essentially to only have this element in there once. Well, it turns out that hashing each individual key is actually incredibly expensive when all you want is to ensure that an element only occurs once. And what we ended up doing on the stream was we used something called a prefix tree, or a trie, where because mounts are essentially just paths, right? There are some string / some string and so on. They actually very, very quickly start to diverge and become unique. And so searching for something in that tree becomes incredibly cheap when having relatively few elements in the tree, which hash maps are great, and they kind of scale really, really amazingly to very large sizes. But in this case, we actually had a very small amount of values in the data structure. And there are probably even better approaches than this. But the reality is, and the only thing that I wanted to show with this is, we need to understand the data structures that we're using so that we can potentially use better ones for a particular purpose. So going back to our example, the first one that I want to show is to avoid memory allocations is escape analysis. And this is something that kind of works in most languages, but the ones where it's most important are garbage collected languages, because in these languages we don't necessarily perform allocations very explicitly. They kind of are done by the runtime for us. And so we need to understand at which point can an allocation happen on the stack, which is very, very cheap, versus when does it happen on the heap. Like I said, this does happen in like C++ and everything as well. But in garbage collected languages, this is particularly important to understand. So let's have a look at our example. Now that we have our benchmark, we have our benchmark, we have our baseline. Now let's try to understand where in this case, and I'm going to do a very quick trick to reveal where escape analysis is failing us. I'm just going to quickly copy this function, and because if I don't do this, Go won't output it for a standard lib function for me, but here we go. So what I just did over here is I told Go not to run the benchmark. All I wanted to do is compile it. And this particular flag tells us to output the escape analysis to standard out. And what we can see over here is that on line number 76, this operation escapes to heap. So let's have a look at what this function actually does. So first, let's kind of read over this function in general. So what it does is it opens the file. Sounds good. It stats it so that we know what the size of this file is. Then it performs a small optimization because computers. And then we actually do this allocation that escapes to heap. Now, why does this escape to heap? The problem is we don't know what the size of this allocation, the bounds of this allocation. It can be anything. It will be however large the underlying file is. And so that's why the compiler decides this particular operation is going to go to the heap, because I can't ensure that the stack is going to be big enough to hold this. And so what this means is, in practice, our file actually contains only a number. We know that about our workload. And so we can actually limit the amount of bytes that we may possibly read. And so let's try to do that ourselves. So we're going to open the file just like the read file function did. We're going to handle the error. We're going to close the file as well when we exit the function. And now we're going to allocate a buffer that is only 64 bytes large, because the number that we're reading is the amount of memory that could possibly be in a computer. And so 64 characters are plenty to describe the amount of bytes that a computer may use in terms of memory. So that's how we're limiting, and hopefully the escape analysis is going to agree with us, how much needs to be allocated. So now we're going to read everything and change this. And sorry, it's not read all, it's read full. Oops. And we need to actually make sure that the buffer is then limited to the amount of bytes that we've actually read. So now we can put this through our escape analysis again. And it says to escape to heap. Why does it say that? Then let's do this. All right. Now we can see make byte 64 does not escape. I'm actually not sure why the other one would have escaped to heap. This was the one that I practiced in my practice run, but we could figure this out after the talk as well. I might have actually looked at the wrong line. Sorry about that. So this does not escape to heap, and this is exactly because we're limiting the amount of memory that's being allocated. We can ensure that 64 bytes can fit onto the stack. So we've actually eliminated a memory allocation. So let's see whether running our benchmark actually confirms this. So we're rerunning this, and anybody who kind of remembered the number of nanoseconds that we used previously may already start to see a difference. And we can see just by preventing this one memory allocation, we have just reduced the runtime of this by 17%. So as we can see, and like I said, memory allocations tend to be a very, very expensive operation. This made a huge difference. And so 17% of something that in total, I didn't show this earlier, but in total, this particular function uses almost 20% of all CPU time within containerd. I only showed one of the code paths earlier. But 17, let's round up and say 20% of 20%. We've just optimized like 4% of the entire CPU time of this process that runs on probably tens of millions of machines worldwide. So this makes a real difference to all the machines on the planet. So escape analysis, very, very important. Like I said, this is something that Java does. This is something that Go does. This is something that you may even want to have a look at with like GCC or Clang, a very important technique to learn. Now, the next one, and this happens to apply to memory allocations as well, but you could also generalize this as batch operations when you can. Turns out computers are actually much better at performing the same task in batch than many times in small batches. And so in this particular case, I pre-allocate a list where I then end up just writing to this list that I've once pre-allocated 1,024 items to. Ideally, I know exactly how many to pre-allocate, but it could also, if I just know, everything always ends up allocating at least 1,000 items, that can also be a good, guesstimate. Ideally, we always pre-allocate exactly what we need. But oftentimes, just pre-allocating some can also make a huge difference. Now, the next one is memory reuse. In this particular case, on the left-hand side, we have a component that just hashes whatever content you give it. And we happen to use SHA-256. We write the content, and we just sum it up. So all good. Very, very, very simple. The problem is, if we were to look at profiling data of this, on line number 8, where h.sum is being called, it allocates a new slice every single time to write all of the result into. But it already gives us the ability to reuse byte slices here. So on the right-hand side, what we're doing is we just keep reusing the same buffer every time when we hash this content. Now, this is not necessarily something that's thread safe. If you use this in a concurrent manner, this would be a problem. But if not, this is a very good optimization. If we were in a setting where we have concurrency, you may want to use a buffer pool that actually is concurrency safe. So in this particular example, we do exactly the same thing, except every time we require a byte slice, we take it from the buffer pool, we do all of our operation, and then we put it back when we're done. So various types of memory reuse. Now we're at the point where we've kind of exhausted all of our memory allocations, we're using the right data structures, we're using the right algorithms. Now we come to the point where is our compiler actually outputting code as optimally as it possibly can? And one of the really interesting optimizations that compilers perform is called inlining. And I have an example here. So I'm using a tool that shows us the assembly code that our Go code ends up producing. So what we have here is just a main function that acquires a first random integer, a second random integer, and then what we can see here is, and I forced the compiler not to inline this because typically it would have decided to do that, but for the sake of demonstration, I wanted to show this. We have a function called add that will just add the two integers together and return the result. In this case, I've forced not to inline. So what it does is it sets up our stack. It moves R0 and R1, which were previously the numbers that were being over here, sorry, if we're scrolling down here. So this is the random function, and we can see it writes into R1 and R2. And so this function, all it does is, within the main function, all this does is it prepares the stack, so it pushes these two values onto the stack, and then we can see call main.add. And then that function, as we can see over here, all it does is truly just calls the assembly add function and returns. Now, it turns out doing this many times is actually really expensive. Pushing something onto the stack, doing a very cheap operation, and then kind of cleaning up the stack again. And so compilers for a very long time have been using this optimization called inlining, where based on heuristics, they decide, is it actually worth setting up the stack, calling this function, getting the result, and tearing down the stack again? Well, in this case, the compiler decides, no, this is absolutely not worth it. This function is super cheap to execute, and so the added overhead of setting up the stack and tearing down the stack is just not worth it. So we don't care. We'll have a slightly bigger binary because this can maybe inlined in multiple places in our code, but it's just worth it for the sake of performance. So inlining actually turns out is a very important optimization, and basically our programs would never perform very well if compilers didn't perform inlining, because it's almost like economy of scale. It happens so often, even though the performance gain of a single inlining call is very small, because it happens thousands, maybe tens of thousands or millions of times, it actually adds up. And one really cool thing, like I said, inlining tends to happen based on cost heuristics. So it decides, this function is cheap to execute, but that's just, how do we actually know that, right? The compiler just does kind of a guesstimate. And there's a really cool tool called profile-guided optimizations, where you're giving the compiler profiling data about your actual execution of production code, and it can use that to make opinionated decisions for inlining, for example. Let's say this is a very hot function that ends up getting called all the time in your code. So we know, even though this function has a large complexity, in this case, it actually makes sense to inline it. And profile-guided optimizations helps the compiler understand when that is actually a better decision to make. The last but not least, and hopefully your compiler does some of this as well, but this should be only the absolute last resort. So SMID stands for single instruction, multiple data, and essentially these are extensions to CPUs that allow you to do many operations one operation on multiple pieces of data. So these are some of the most widely used extensions. For example, SSE2 allows you to do operations on 128 bits of data. One really commonly used one is the one that I enumerated here, which is comparing 16 8-bit integers all at once. And in order to get into SMID programming, you kind of need to rethink and rewire your brain, because this is not the way that we've kind of learned to program. It's really about looking at multiple data points at once. But once you've kind of exhausted all the other things, you have the right algorithms, you have the right data structures, you don't have, or you have the memory allocations you absolutely have to have, this is the last resort where we can do multiple things at once, essentially. If you're really interested in learning more about this, I highly recommend checking out Daniel Lemir's blog. He kind of regularly blogs about various optimization techniques that he's performed using SMID instructions. So, kind of going back, we kind of now have all the tools in order to beat Moore's law, right? Or the end of Moore's law. And let's kind of think back one more time. We need to profile, we need to benchmark, and we use all of these tools to then actually make meaningful changes. And like I said, we want to make sure our approach is the right one, our data structures are the right ones, the algorithms are the correct algorithms for the problem at hand. We remove allocations. We help our compiler make the right decisions. And last but not least, we do multiple things at once. And once we've actually conquered this, and this is actually just something that happened yesterday on the left-hand side here, just by doing these things systematically with a always-on profiler, we at Polar Signals happen to reduce our CPU spend by 25 to 50% almost every week, right? It's crazy how much difference this can make when you're very systematic about doing this. So now we have the tools to deal with the end of Moore's law. So with that, have fun optimizing code.